quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in. Let the outside world dissolve and gently descend into tonight's world. The Drake equation is not a prophecy. It is a framework built to help people talk clearly about a question that is easy to feel but hard to measure. How many civilizations might exist in our galaxy that could communicate? It was written in an era when humans had not yet found a single exoplanet, when radio astronomy was young, and when the idea of listening for signals from other stars still felt like science fiction. Yet the equation survived because it does something calm and useful. It breaks a giant unknown into smaller unknowns. It forces us to name what we do not know, what we can estimate, and what we might one day measure. Tonight, we go through the story of the Drake equation. We begin in the middle of the 20th century, when the sky was changing in a new way. For thousands of years, humans watched the stars with naked eyes and simple lenses. They mapped the motions. They told stories. They guessed. Then, in the early 1900s, radio began to spread across Earth. By the middle of the century, radio had become not just a tool of war and commerce, but a new kind of sense. It made the invisible visible. It allowed scientists to detect the universe in wavelengths our eyes cannot see. Radio astronomy was born from both curiosity and necessity. Radar and communications research built equipment and knowledge. After World War II, some scientists began to point those tools upward. They discovered that the sky was not silent. The sun produced radio noise. The Milky Way glowed in radio. There were bursts and steady sources. The universe had its own station. At the same time, another thought was spreading. If radio is a powerful way to send information, and if human technology can spill signals into space, then another civilization might do the same. If so, the galaxy might be full of faint whispers. You would not see them. You would listen. This idea became the seed of what we now call SETI, the search for extraterrestrial intelligence. But in the late 1950s and early 1960s, SETI was not a large organized program. It was a bold idea discussed by a small number of people. The question was not only scientific, it was cultural. It challenged the old picture of humans as the only thinking beings. Frank Drake was one of the key figures who helped turn the question into an experiment. He was a radio astronomer with practical skill, not only big imagination. He understood antennas and receivers. He understood noise and signal. He understood that the first step in a search is not to believe, but to define what you are actually looking for. In 1960, Drake carried out a pioneering search sometimes described as the first modern radio SETI experiment. He aimed a radio telescope at two nearby sun-like stars in the general direction of a frequency region considered quiet and interesting. The details of this early search are often simplified in retellings, but the core idea matters. Drake tried to see if there were narrowband radio signals that could not be explained by natural sources. The search did not find an alien transmission, but it did something else. It showed that the question could be approached with equipment, time, and careful methods. It brought the problem out of pure speculation. Soon after, a meeting was planned to discuss the broader question. The setting often mentioned in the story is the Green Bank Observatory in West Virginia. The participants included scientists and thinkers who wanted to ask, in a serious way, what it would take to estimate the number of communicative civilizations. Here is where the Drake equation enters. The story is often told like this. Drake wanted a way to organize discussion. People could argue endlessly about aliens without structure. So he wrote a simple equation on a board. It was not meant as a final answer. It was a tool for conversation. It was a list of factors. In its classic form, the Drake equation is written as a multiplication of terms. Each term represents a fraction or rate. When you multiply them, you get a number, often called n, the number of civilizations in the Milky Way capable of communicating in a way we might detect. The exact letters vary depending on how it is written, but the usual structure is steady. First, a rate for how often stars form in our galaxy. Then, a fraction of those stars that have planets. Then, a number of planets per system that could be suitable for life. Then, a fraction of those that actually develop life. Then, a fraction where life becomes intelligent. Then, a fraction where intelligent life develops technology that produces detectable signals. Then, a length of time that such a civilization remains detectable. At first glance, it looks simple, but inside each term is a deep unknown. So tonight, we will treat the Drake equation like a case file. We will walk through the origin story, what each term means, what we have learned since Drake wrote it, and why the equation is still discussed, even though it cannot be solved in the way a normal algebra problem can. We will keep the tone calm and documentary. We will avoid extreme claims. We will treat the equation as a mirror. When we look into it, we see both the universe and ourselves. The first term is often written as the rate of star formation in the Milky Way. This is a number with units, like stars per year. It asks, in a steady way, how many new stars are born in our galaxy over time. In Drake's era, this number was uncertain. Today, it is still not perfect, but it is constrained. We can observe star-forming regions. We can estimate the mass of gas turning into stars. We can model the history of the galaxy. Even so, this term matters less than some later terms, because it is not wildly uncertain. It is not likely to vary by orders of magnitude in the way the biology terms might. The next term is the fraction of stars that have planets. This is one of the places where the modern era changed the equation dramatically. In the early 1960s, there were no confirmed exoplanets. People debated whether planetary systems were common. Some models suggested planets might be rare. Others suggested they might be common, but there was no direct evidence. Then, over the following decades, exoplanets began to be detected. At first, they were surprising types of planets, like giant worlds close to their stars. Over time, detection methods improved. The Kepler Space Telescope, in particular, revealed something that reshaped our view. Planets are common. Many stars have them. It is now reasonable to think that most stars in the Milky Way host planets. This does not solve the Drake equation, but it stabilizes one of its early terms. The next term is the number of planets per system that could support life, sometimes framed as Earth-like planets, or planets in the habitable zone. Here we must slow down, because the phrase habitable zone is often misunderstood. The habitable zone is not a guarantee that a planet is habitable. It is a region around a star where, in principle, liquid water could exist on the surface, given certain atmospheric conditions. It is a temperature argument. But life depends on more than temperature. A planet might be in the habitable zone and still be sterile. It might have no atmosphere. It might have extreme radiation. It might have a runaway greenhouse effect. It might be locked with one side always facing its star. It might have water only deep underground. So the Drake equation term here is a placeholder for a complex concept. How many environments are actually suitable for life as we understand it? In Drake's time, people could only guess based on our own solar system. Today, we have thousands of exoplanets, but we still struggle to measure their atmospheres directly in the detail needed. We can estimate the frequency of Earth-sized planets in certain orbits. We can estimate how common rocky planets are. We can also observe that many planets exist in systems very different from ours. So this term remains uncertain, but it is no longer pure imagination. Now we enter the biological terms, and this is where the equation becomes less like astronomy and more like a story about life itself. The next term is the fraction of suitable planets where life actually emerges. This is one of the hardest terms. We have exactly one confirmed example of life: Earth. We do not yet know whether life is a common chemical outcome or a rare accident. We know that life on Earth appeared relatively early in the planet's history. That fact can be read in two ways. One reading is optimistic. If life appeared quickly, maybe it is easy. Another reading is cautious. We only observe Earth because it produced us. We do not see the planets where life did not appear. This is a kind of selection effect, so we must be careful. We can study how life might begin. We can study chemistry. We can create experiments with organic molecules. We can study hydrothermal vents. We can study how complex molecules form in space. But we still do not have a complete path from non-life to life. So this term stays open. The next term is the fraction of planets with life where intelligent life emerges. Here again, we have only one sample. Earth had life for billions of years before a technological civilization appeared. Most life on Earth is microbial. Complex life took a long time to develop. Intelligence, in the sense of building radio telescopes, appeared in one species, at least so far. This suggests that intelligence might be rare, but it could also be that intelligence is one of several possible pathways. Octopuses show problem solving. Crows show tool use. Dolphins show complex communication. Great apes show planning. So intelligence might not be a single step, but a gradient. The Drake equation term is not about intelligence in a broad sense. It is about a kind of intelligence that builds technology capable of producing detectable signals. So the next term is the fraction of intelligent species that develop such technology. Here, humans are again a single example. We developed radio within a short time after industrialization. We developed radar and broadcasting. We also developed the ability to produce strong, narrowband signals and powerful radars that could be detectable at distance. But we also developed technology that is quieter in some ways, like fiber optics and directional communications. This means that detectability might not be constant. A civilization might be loud for a short time, then quiet. Or it might be quiet until it chooses to send a beacon. Or it might communicate in a way we cannot recognize. So the fraction term and the detectability term can overlap. Finally, the Drake equation includes a term for how long such a civilization remains detectable. This is often called L, the length of time. This term matters enormously because it can change n by huge amounts. If civilizations tend to be detectable for only 100 years, the galaxy might have few detectable civilizations at any given time. If they remain detectable for 1 million years, then many could overlap. This is also where the equation touches fear and hope, because the length of time a civilization remains detectable is tied to survival. Will it destroy itself? Will it collapse? Will it choose silence? Will it move to technologies we cannot detect? Will it spread beyond its planet? So the Drake equation is not only about aliens, it is also about what it means to endure. Now we can see the shape of the equation as a story. Astronomy gives us stars and planets. Biology gives us life. Evolution gives us intelligence. Culture gives us technology. History gives us survival. When you multiply those together, you get a number that is not a prediction, but a reflection of our assumptions. If you assume life is common and survival is long, n can be large. If you assume life is rare and survival is short, n can be small. The equation allows both because it is not yet constrained by enough data. This is why the Drake equation is sometimes criticized. Some say it is too uncertain to be useful, but that criticism misses its purpose. The Drake equation was never meant to be solved immediately. It was meant to guide research and clarify debate. It tells us which questions matter. It tells us what we should try to measure. And it gives us a way to separate disagreements. Two people might disagree about aliens, but the equation forces them to say where. Do you disagree about how common planets are? Do you disagree about how common life is? Do you disagree about how long civilizations last? That is progress. Now we move forward in time because the story of the Drake equation is also the story of how our knowledge changed. In the decades after Drake, SETI grew and shrank in public attention. Sometimes it was funded. Sometimes it was mocked. Sometimes it was cut. The search itself had practical challenges. The galaxy is large, signals weaken with distance, natural sources produce noise, human technology produces interference. The number of frequencies to search is huge. The number of stars is huge. So SETI had to choose strategies. One strategy was to look at nearby sun-like stars. Another was to look for a special frequency region, sometimes called the water hole, between certain hydrogen and hydroxyl frequencies, where natural cosmic noise is relatively low and the association with water is symbolically interesting. Another strategy was to look for narrowband signals, because nature rarely produces very narrowband continuous tones. Over time, SETI also expanded to consider other kinds of signatures, not only radio, but optical flashes, not only deliberate messages, but leakage, not only communication, but technosignatures, like waste heat or unusual atmospheric chemicals. This expansion changes how we think about the Drake equation terms, because detectability is not a single concept. Now we should address a question that often appears whenever the Drake equation is discussed. If the galaxy might contain many civilizations, why do we not see them? This is often called the Fermi paradox, after the scientist Enrico Fermi, who is associated with the question, where is everybody? The paradox is not a formal proof. It is a tension between two ideas. One idea is that the galaxy is old and large, so advanced civilizations could exist. The other idea is that we do not see clear evidence. If civilizations were common and expanded, we might expect some sign. So why is there no sign? The answer could be simple. Maybe civilizations are rare. Maybe life is rare. Maybe intelligence is rare. Maybe technology is rare. Maybe civilizations do not last. Or the answer could be complex. Maybe civilizations exist but do not travel. Maybe they travel but leave little trace. Maybe they are quiet. Maybe we are not looking correctly. Maybe we are early. Maybe the signs are subtle. The Drake equation does not solve the Fermi paradox, but it gives it structure. If you think the paradox is strong, you might assign small values to certain terms. If you think the paradox is not decisive, you might assign larger values. Now we return to the story of the equation itself, because it has a human origin. Frank Drake did not claim that his equation was final truth. He used it as a discussion tool. Over time, the equation became famous. It appeared in textbooks and documentaries. It became a symbol of scientific curiosity. But symbols can become distorted. Some people treat the equation as if it predicts a number like 10,000 civilizations. Others treat it as if it proves there are none. Both are mistakes. The equation only gives a number after you choose inputs, and the inputs, especially the biology and survival terms, are uncertain. So a responsible approach is to treat the equation like a map of uncertainty. Now we can deepen each term with modern knowledge. We already discussed that planets are common. That is one of the biggest updates. We can also say that small rocky planets are common. We can say that many stars are long-lived. We can say that water and organic molecules exist widely. We can say that habitable conditions might exist not only on planets, but on moons, and perhaps in subsurface oceans. This widens the possible places for life. On the other hand, we can also say that life requires stability. It might require plate tectonics. It might require a magnetic field. It might require a stable climate. It might require protection from radiation. It might require a certain chemistry. So the number of truly suitable worlds might be smaller than the naive count. Now consider intelligent life again. On Earth, complex life and intelligence were shaped by contingency. Mass extinctions changed the path. Continents moved, climate shifted, random events mattered. So intelligence might not be a guaranteed endpoint. The Drake equation does not tell us whether intelligence is inevitable. It only forces us to consider that question. Now, consider technology. Even if a species is intelligent, technology is not guaranteed. Technology requires certain conditions. It requires access to materials. It requires stable social structures. It requires the ability to transmit knowledge. It requires energy. It requires time. A species could be intelligent and still remain non-technological, or it could develop technology that is not radio-based, or it could develop technology but choose not to broadcast. So the term for communicative technology is also uncertain. Finally, the length term. This term is often where people place their hopes and fears. If you assume civilizations destroy themselves quickly, you get a small n. If you assume civilizations stabilize and last, you get a large n. What does Earth suggest? We have been radio loud for about a century. We have developed powerful radars and transmissions, but we are also moving toward quieter communications. We are not sure how long we will remain detectable, so even for ourselves, L is uncertain. Now we can pull back and ask what the Drake equation has done for science. It has influenced how scientists talk about SETI. It has encouraged exoplanet research. It has connected astronomy to biology. It has helped shape astrobiology as a field, and it has provided a cultural bridge. It lets the public talk about aliens in a structured way. Now, a careful documentary must also include the main objections. The strongest objection is that without data, The equation can produce any answer you want. That is true in the sense that the terms can vary widely, but it is also true that some terms are now constrained. We know planets are common. We know star formation rates. We can estimate the frequency of rocky planets, so the equation is not completely free. Another objection is that the equation assumes civilizations communicate in ways we can detect. This is also true, but an equation has to assume something to be meaningful. The Drake equation is explicitly about detectable communication. It does not claim to count all intelligence, so the objection is a reminder of scope, not a fatal flaw. A third objection is that multiplication of uncertain terms can be misleading, because small uncertainties compound. This is true. If each term is uncertain by a factor of 10, then the final result can be uncertain by a factor of 10 to the power of the number of terms. This is why careful use of the equation focuses on ranges and distributions, not single numbers. In modern discussions, people sometimes assign probability distributions to each term and simulate outcomes. This can show what assumptions matter most. Often, the length term dominates. Often, the life and intelligence terms dominate. Now we can also talk about why the equation remains compelling, even when we admit it cannot be solved today. It remains compelling because it captures a human urge. We want to know whether we are alone. We want to place ourselves. We want to know whether intelligence is common. And the equation makes that urge speak in numbers, which feels like control. But the deeper truth is that the Drake equation is an honesty tool. It makes us admit we do not know. Now we can enter the modern era again and ask how the next decades might change the equation. Exoplanet studies will refine how common Earth-like planets are. Atmospheric studies might detect biosignatures. If we detect a biosignature, the life term becomes less uncertain. If we detect a technosignature, the intelligence and technology terms become less uncertain. If we detect nothing after many careful searches, that might push some terms lower. But negative results are tricky. Not finding a signal does not prove no one is there. It might mean we looked in the wrong way. It might mean signals are rare. It might mean civilizations are quiet. So the equation remains, waiting for evidence. Now, we can tell the story of the Drake equation in another way, as a story about what science does when it meets deep uncertainty. Science does not only collect facts, science also builds frameworks. Frameworks help us decide what to measure. Frameworks help us talk without drifting. The Drake equation is one of those frameworks. It is like a checklist for a mystery. Stars, planets, habitability, life, intelligence, technology, time. If you have to write a question on a board and build a search program from it, you need such a list. So even if the equation never gives a final number, it has already done its work. Now we can soften our pace and approach the end of the story. Imagine the meeting room, a board, a group of scientists, a question that could easily become a debate with no end. Drake writes the equation. The room becomes quiet for a moment, not because the answer is there, but because the problem is now shaped. It has edges, it has parts, it has a way to be approached. That is the moment when the Drake equation becomes more than a formula. It becomes a story about how humans face the unknown. And now, as rain continues outside and the night continues to deepen, we let the equation settle into its true role. Not as a promise, not as a trick, but as a calm structure for wonder. We can go deeper, because the Drake equation becomes clearer when we treat each term like its own miniature documentary. Each term has a history, each term has arguments, each term has modern evidence that did not exist when Drake first wrote the list. So we return to the first term, the rate of star formation in the Milky Way, and we ask what it really represents. The galaxy is not a static city of stars. It is a living structure. Gas clouds collapse. New stars ignite. Massive stars burn fast and die. Smaller stars burn slowly and persist. Over billions of years, the mix changes. A galaxy like ours has a long history. Early on, star formation may have been higher. Over time, it can slow as gas is used up or heated. But even now, star formation continues in spiral arms and dense clouds. Why does this matter for the Drake equation? Because the equation is often interpreted as the number of civilizations in the galaxy right now. If stars form at a certain rate, then over long times, the galaxy produces many chances for planets and life. But the rate term is not the main source of uncertainty. It is a steady foundation. The next term, the fraction of stars with planets, used to be a huge unknown. Now it is not. Here the story is one of measurement. At first, astronomers could only infer planets from subtle effects. One method is called radial velocity. A planet and a star orbit a common center of mass. The star wobbles slightly. That wobble can be detected as a shift in spectral lines. The earliest exoplanets detected by this method were massive and close to their stars, because those cause the largest wobble. Another method is called transit detection. If a planet passes in front of its star, it blocks a tiny amount of light. This produces a regular dimming pattern. The Kepler mission was designed to watch many stars and detect these dips. Kepler did not just find planets. It revealed that planets come in many sizes and orbits, and that they are common. This transformed the Drake equation because it moved us from guessing to counting. We can now say with reasonable confidence that planets are not rare exceptions. They are part of normal star systems. But then we meet the next term. How many of those planets are in environments where life could exist? Here, the story becomes more complicated, because habitability is not a single property. A planet can have the right temperature range, but lack a stable atmosphere. A planet can have water, but be sterilized by radiation. A planet can be rocky, but have constant volcanism. A planet can be in a safe orbit, but be hit by frequent catastrophic impacts. A planet can orbit a small red dwarf star and be within the habitable zone, but red dwarfs can be active, producing flares and strong radiation that might strip atmospheres. On the other hand, red dwarfs are very common and long-lived. If life can adapt, red dwarfs could host many habitable worlds. So in modern discussions, this term becomes a set of questions. How common are rocky planets? How common are stable atmospheres? How common is liquid water? How common are long-term stable climates? How common are protective magnetic fields? How common are large moons that stabilize axial tilt? And the honest answer is that we do not yet know. We can model, we can observe, we can estimate, but we cannot yet survey atmospheres at scale. This is where future telescopes matter. If we can measure the composition of many exoplanet atmospheres, we can begin to constrain habitability. Now we reach the most uncertain term for many people, the fraction of habitable worlds where life actually begins. This term is sometimes called abiogenesis, the origin of life. It is one of the deepest questions in science. On Earth, life began early. The planet formed about 4.5 billion years ago. Evidence suggests life existed by at least 3.5 billion years ago, possibly earlier. That seems quick on cosmic timescales. If life begins quickly when conditions allow, then the fraction might be high. But there is a trap here. We observe an inhabited planet because we are here. We cannot sample the planets where life did not begin. So the early appearance of life could be a selection effect. Still, we can look for hints. We can study chemistry that produces amino acids and other building blocks. We can study how complex molecules form in space. We can study how lipids form membranes. We can study how RNA might arise. We can study hydrothermal vents, where chemical gradients provide energy. These studies suggest that the ingredients for life are not rare, but ingredients are not the same as a living system. A living system is not just chemistry. It is organization, replication, and evolution. So the term remains uncertain. Now the intelligence term, this is where the Drake equation becomes especially emotional, because it touches what we think intelligence is. On Earth, life is abundant. Complex life exists. But technological intelligence is rare in the sense that only one species built radios. Some argue that intelligence is a convergent outcome. They point to multiple lineages that evolved complex brains. Others argue that our path was contingent. They point to the long chain of events required, including the right kind of environment, stable continents, and the right evolutionary pressures. A careful view is that we cannot yet assign a confident number. We can say that intelligence is not impossible. It happened at least once. We can also say it is not guaranteed. Earth had life for billions of years without it, so the fraction could be low. Now the technology term. Even if a species is intelligent, technology might not follow. Technology requires a pathway to control fire, create tools, transmit knowledge, and develop industry. It also requires access to energy. A civilization in a water world might have difficulty developing metallurgy. A civilization under an ice shell might be trapped. A civilization might use biology rather than machines. A civilization might have ethics that discourage broadcasting. So detectability is not the same as intelligence. Now the length term, again. This term is sometimes treated as the main source of uncertainty. It is also often tied to the idea of a filter. Some people discuss a concept called the Great Filter. The idea is that there might be a step in the chain from dead matter to galaxy-spanning civilization that is extremely hard. If that step is behind us, then we are rare but lucky. If that step is ahead of us, then we may be in danger. The Drake equation does not require the Great Filter concept, but the length term and the intelligence term are places where such thinking often lands. This is where the equation becomes a story about risk, because L depends on whether civilizations survive. It depends on whether they avoid self-destruction. It depends on whether they manage resources. It depends on whether they handle conflict. It depends on whether they adapt to their star and planet. So when people argue about L, they are often really arguing about what kinds of futures are possible. Now we can build a calm example, not as truth, but as illustration. Suppose the Milky Way forms a couple of new stars per year. Suppose most of those stars have planets. Suppose a fraction of those planets are in environments that could support life. Suppose life begins on some fraction. Suppose intelligence arises on some fraction. Suppose technology arises on some fraction. Now suppose the average detectable lifetime is 10,000 years. Then, over the lifetime of the galaxy, there could have been many civilizations, but at any given time, only a limited number overlap. And if the overlap is small and the galaxy is huge, the distance between civilizations could be very large. Signals could be weak. Messages could take centuries. So even if n is not tiny, contact could still be difficult. This is another reason the Drake equation does not automatically imply that we should have already found someone. The galaxy is not a small room. It is a vast wilderness. Now we should connect the Drake equation to one of the biggest modern shifts in astronomy, the move from thinking about planets as rare to thinking about planets as abundant. When planets were hypothetical, discussions about life were abstract. Now with thousands of exoplanets, the discussion becomes grounded. We can point to a planet that is roughly Earth-sized. We can point to a planet in a habitable zone. We can point to a system with multiple planets. We can point to a world around a red dwarf. We can point to a world in a compact system. This changes the emotional tone of the Drake equation. It becomes less like a dream and more like a census we have not finished. But we also must admit what we cannot yet do. We cannot yet take close-up images of Earth-sized worlds in most cases. We cannot yet read their surface biology directly. We cannot yet detect cities. We cannot yet detect radio signals from most planets. So the equation is still a framework, waiting for better instruments. Now we can discuss how scientists think about possible signs of life and technology. A biosignature is a sign that suggests biology. It might be a gas in an atmosphere that is hard to sustain without life. It might be a pattern of seasonal change. It might be a surface reflectance feature. But biosignatures can have false positives. A planet can produce oxygen by non-biological processes under some conditions. A planet can produce methane by geology. So even if we detect a biosignature, interpretation is hard. A technosignature is a sign of technology. It might be a narrowband radio signal. It might be a powerful laser flash. It might be an unusual chemical pollutant in an atmosphere. It might be waste heat from large-scale energy use. It might be an artificial structure producing a specific transit pattern. These ideas expand the Drake equation beyond radio. If we broaden detectability, then the technology term changes. A civilization might be detectable through its industry, not its communication. But these ideas also have limits. We might not recognize the sign. We might confuse it with natural phenomena. So the equation remains a guide rather than an answer. Now, since this is a documentary story, we should include the human motivations that surrounded the Drake equation. The early SETI era was shaped by the Cold War. It was a time of rapid technological growth. It was a time of anxiety about extinction. It was also a time of optimism about science. Spaceflight began. The first satellites launched. Humans walked on the moon. In that context, the idea of other civilizations felt plausible. If we could build radio telescopes and rockets, perhaps others could too. So the Drake equation was both a scientific tool and a cultural artifact. It captured a moment when humans were suddenly capable of listening beyond Earth. Now we can also address a common misunderstanding. Some people think the Drake equation is a claim that alien civilizations exist. It is not. It is a way to think about how many might exist, conditional on assumptions. It does not guarantee contact. It does not guarantee that life is common. It simply organizes the question. Another misunderstanding is that the equation is meant to be solved precisely. It is not. It is meant to be updated as knowledge improves. The planet term is a perfect example. In Drake's era, it was a guess. Today, it is constrained. So the equation can evolve. Now we can add one more layer that often appears in discussions. The idea that the equation is too optimistic or too pessimistic, depending on how you write it. Some versions of the equation split terms differently. Some include a term for the fraction of life that becomes complex. Some include a term for the fraction of planets that remain habitable long enough. Some include a term for the fraction of signals that are detectable by our methods. These variations are not mistakes. They reflect the fact that the question can be decomposed in multiple ways. The key is to be explicit. If you change the terms, you should explain why. Now we can return to the emotional center again, because the Drake equation is a story about loneliness. Humans are social creatures. We look at the night sky and we wonder if we are alone. We wonder if others have looked back. We wonder if there is a conversation happening without us. The Drake equation allows that wonder to be spoken in a sober language. It allows us to say calmly that there are steps required. It allows us to say that even if life is common, contact might be hard. It allows us to say that our own survival matters. Now we can also consider how the equation can be used responsibly. A responsible use does not pick a single number and declare victory. A responsible use explores ranges. It explains uncertainty. It admits that some terms are unknown by orders of magnitude. It uses the equation to highlight research priorities. For example, if you think the life term is the biggest unknown, you might prioritize looking for biosignatures. If you think the length term is the biggest unknown, you might prioritize studying existential risks. If you think the technology term is the biggest unknown, you might broaden the search for technosignatures. So the equation can guide action. Now we can close the file with a final, calm perspective. The Drake equation is famous because it looks like a simple formula, but in reality, it is a list of mysteries. Each letter stands for a field: astronomy, planetary science, geology, chemistry, biology, evolution, sociology, history, and perhaps something we do not yet have words for. If we ever answer the question of how many civilizations exist, it will not be because we solved an equation on a board. It will be because we measured the universe more deeply. We will detect more planets. We will detect atmospheres. We will detect signs of life. Or we will detect silence across a wide enough search to force new conclusions. Until then, the Drake equation remains what Drake intended: a calm tool for thinking, a way to speak honestly about the unknown, a structure that holds wonder without letting it spill into fantasy. And as the rain continues and your thoughts slow down, you can let that structure be gentle, not an answer, just a way to hold the question. We can stretch the timeline a little wider, because the Drake equation sits at a crossroads of older ideas. Long before Drake wrote his equation, people asked whether other worlds were inhabited. Philosophers in ancient times argued about many worlds. In the modern era, as telescopes improved, the question became more concrete. People imagined canals on Mars. They imagined lush Venus. They imagined a solar system full of neighbors. Then, science corrected those images. Mars was cold and thin-aired. Venus was a furnace with crushing pressure. The solar system became quieter. At the same time, the scale of the universe became larger. We learned that stars are suns. We learned that the Milky Way is only one galaxy among many. The number of possible worlds became enormous. So the question did not die. It changed shape. Instead of asking, are there people on Mars? We began to ask, are there civilizations somewhere in the Milky Way? Radio made that question practical. This is why the Drake equation is a product of its era. It belongs to the moment when humans first had a tool that could, in principle, detect another civilization across interstellar distance. Now, to make the equation feel more real, we can walk through each term again with modern examples. When we say stars form, we can picture star nurseries, dense clouds where gravity pulls gas into knots. Some knots ignite and become stars. Some become massive stars that live short, bright lives. Some become red dwarfs that can last for trillions of years. When we say planets are common, we can picture the protoplanetary disks around young stars seen by modern telescopes. We can picture dust grains clumping, then rocks, then worlds. We can picture that the same process that formed Earth is not unique. When we say habitable environments, we can picture not only Earth, but also the idea of subsurface oceans. In our own solar system, moons like Europa and Enceladus may hold liquid water under ice. That means life might not need a surface ocean in sunlight. It might live in darkness, fed by chemistry. If that is true, the number of possible life-bearing environments increases. But then we hit a hard fact. Even if microbial life is common, technological civilization might not be. We can imagine a galaxy full of oceans with simple life. We can imagine a galaxy where life rarely becomes complex. We can imagine a galaxy where intelligence arises but remains local and quiet. So when people use the Drake equation, they should be clear about what they mean by life. The equation counts only one kind of life, the kind that builds technology that can be detected. Now we can discuss how scientists sometimes try to handle the uncertainty. One method is to treat each term as a range. For example, instead of saying the fraction of habitable planets where life begins is 0.5, you might say it could be anywhere between 0.001 and 1. Then you see what the final n could be. Another method is to use Bayesian reasoning, where you update beliefs based on evidence. The discovery of many planets updates the planet fraction upward. The lack of detected signals might update the technology or length term downward, but only slightly, because our search is still limited. The future detection of a biosignature would strongly update the life term upward. The future detection of a technosignature would strongly update the intelligence and technology terms upward. So the Drake equation can be a living document. Now, there is also a separate question that often hides inside Drake discussions. Do civilizations need to communicate to be detected? Not necessarily. Even if a civilization is not broadcasting, it might produce waste heat. It might alter its planet's atmosphere. It might build structures. But those signs may be hard to see. If you are looking across light years, a small change can vanish in noise. So detectability becomes a key concept. A civilization could exist and be invisible to our tools, and our tools are still young. We have been looking for only a short time. This is another reason the Fermi paradox is not a final proof of absence. Now, since this project is meant for a calm, long-form episode, we can also include a careful explanation of why the equation is written as a multiplication. The equation multiplies because the steps are sequential filters. If a star forms, that creates a chance. If that star has planets, that reduces the set. If a planet is habitable, that reduces the set. If life begins, that reduces the set. If intelligence arises, that reduces the set. If technology arises, that reduces the set. If the civilization lasts long enough to overlap with us, that reduces the set. Multiplication is a simple way to represent change probabilities, but we should also admit that the steps are not perfectly independent. For example, the kind of star might influence habitability. The kind of planet might influence how life begins. The presence of a moon might influence climate. So the equation is a simplified model, and simplified models can still be useful. Now, we can also tell the Drake story through a single moment. The moment when the equation forces a person to confront ignorance. Ask someone, how many alien civilizations exist? They might answer with emotion. They might say, millions, because the universe is big. Or they might say, none, because we have no evidence. Then you write the Drake terms. You ask how many stars form. They say, a few per year. You ask, how many have planets? They say, probably most. You ask, how many planets might be habitable? They hesitate. You ask, how many of those develop life? They do not know. You ask, how many develop intelligence? They do not know. You ask, how long do they last? They do not know. And suddenly, the conversation becomes honest. That honesty is the real purpose. Now, we can add another angle that often comes up in Drake debates, the rare earth hypothesis. This is the idea that while microbial life might be common, complex life might be rare, because it requires a special set of conditions: a stable star, a planet at the right distance, a magnetic field, plate tectonics, a large moon, a giant planet like Jupiter to reduce impacts, a stable climate. If you believe this, you might assign a low value to the terms that lead to complex and intelligent life. But the rare earth hypothesis is also uncertain. We do not yet know how many of those conditions are truly required. We do not know if plate tectonics is necessary. We do not know if a large moon is necessary. We do not know if complex life could arise under different pathways. So the hypothesis is a caution, not a conclusion. Now we can also include another angle, the idea that intelligence might often choose inward focus rather than outward expansion. A civilization might build virtual worlds. It might optimize comfort. It might reduce energy use. It might become quiet. In that scenario, the length term could be long, but detectability could be short. Again, the Drake equation can incorporate that by changing the meaning of L. L is not only lifespan, it is detectable lifespan. Now we can slow down into a final synthesis. If you take nothing else from this story, take this. The Drake equation is not about getting a number that ends the debate. It is about learning what we need to learn to make the debate real. It is about turning a dream into a research program. It is about turning wonder into questions that can be measured. And if the future brings a detection, the Drake equation will not be obsolete. It will become more useful, because each detection would update the terms. A biosignature would update the life term. A technosignature would update the intelligence and technology terms. Multiple detections would allow us to estimate distributions, and even a long silence would update our models. So the Drake equation is like a quiet ledger. It waits, it records, and it keeps us honest. We can also tell the Drake equation story as a sequence of questions that gradually became measurable. At first, almost everything was unknown. How many stars are there? How many are like the sun? Do they have planets? Are those planets like Earth? Does life begin easily? Does intelligence appear often? Does technology follow? Do civilizations last? In the early 1960s, most of these questions could not be answered with data. They were judged by argument and analogy. Then the data began to arrive, slowly. Astronomers improved measurements of the Milky Way. They improved models of star formation. They mapped gas clouds. They learned more about stellar lifetimes. Then, decades later, exoplanets arrived as a flood. And suddenly, one of the biggest terms was no longer a debate. Planets exist. Planets are common. That shift alone changed the emotional weight of the Drake equation. It is hard to explain how dramatic it feels to move from maybe to we have thousands. The first time someone sees the plot of Kepler results and realizes how many worlds are out there, the galaxy feels less like empty space and more like a field of possibilities. But the Drake equation also teaches patience, because even with planets, the next steps remain uncertain. This is where the equation becomes a lesson in humility. We can count planets, but we cannot yet count life. Now, because this episode is about the story, it helps to picture the meeting itself in Green Bank. A group of people, not a huge crowd. Scientists with different specialties. Radio astronomers, biologists, people who understood signals and noise. People who understood how hard it is to separate a real pattern from random chance. The topic was large and risky. In some circles, talking about intelligent aliens could damage a reputation, but the people in the room believed the question was worth asking carefully. Drake needed the conversation to stay grounded, so he built the equation as a conversation rail. You can almost imagine him guiding the room. If someone starts talking about spaceships, he points back to the terms. If someone starts making bold claims, he points back to the terms. If someone starts dismissing the whole idea, he points back to the terms. Because the equation does not allow lazy dismissal, it demands that you say why. Do you believe planets are rare? Then say so. Do you believe life is rare? Then say so. Do you believe intelligence is rare? Then say so. Do you believe civilizations die quickly? Then say so. The equation turns a feeling into a position. Now, we can also add a simple analogy that helps many people understand the equation. Imagine you are trying to estimate how many radio stations are broadcasting in a huge country, but you do not have a radio yet. You might start by asking how many cities exist, then how many of those cities have electricity, then how many have radio technology, then how many choose to broadcast, then how long they keep broadcasting. You would not claim to know the final number, but you would know what questions matter. That is the Drake equation. Now, we can include another modern layer, the difference between signal production and signal detection. A civilization might broadcast, but we might not detect it. Distance matters. Power matters. Direction matters. If a civilization uses narrow beams, we might miss them. If a civilization transmits occasionally, we might miss them. If a civilization transmits in a frequency band we do not monitor, we might miss them. So N is not the number of civilizations in existence. It is the number of civilizations whose signals overlap with our detection window. This means that even if the galaxy contains many civilizations, SETI could still be hard. Now, if we want to be extra careful, we can note that the Drake equation is sometimes used in two different ways. One way is to estimate the number of civilizations that exist now. Another way is to estimate the average distance between civilizations. If n is small, the distance could be huge. If n is large, the distance could be smaller. But distance is not the same as contact. Even if the nearest civilization is only a few hundred light years away, communication would still be slow. And if signals are weak, detection would still be hard. So the equation does not give us a simple expectation of contact. It gives us a set of constraints. Now we can end with a final calm statement about what the equation means today. Today, we are in a strange middle era. We have discovered that planets are common. We have begun to measure the chemistry of some distant worlds. We are building instruments that might detect biosignatures. We are expanding SETI beyond radio, but we still have not found a clear sign. So we remain in the framework stage. The Drake equation is still doing its original job. It is still a board in a quiet room. It is still a list of questions. It is still a way to hold the unknown without letting it become either denial or fantasy. And because this is a quiet archive, we can do one more careful thing. We can practice the difference between a number and a range. When people hear an equation, they want a single answer. They want one value for each term. But the responsible way to use the Drake equation is to admit that many terms are uncertain and should be expressed as ranges. For example, star formation might be roughly a few stars per year, not exactly a precise integer. The fraction of stars with planets might be close to 1, not exactly 1. The fraction of planets that are truly suitable for life might be small or moderate, depending on how strict your definition is. The fraction where life begins could be extremely small or close to 1. We do not know. The fraction where intelligence arises could be extremely small or moderate. We do not know. The fraction where technology becomes detectable could be small or large. We do not know. The detectable lifetime could be 100 years, 10,000 years, or 1,000,000 years. We do not know. So instead of a single n, the Drake equation produces a cloud of possible n values. In modern thinking, you can imagine rolling dice for each term, but the dice are not fair, and the number of sides is unknown. Some dice might have a few likely outcomes. Some might have huge uncertainty. That is why the equation is often more useful as a tool for asking, which dice matter most? If you discover that the final result is most sensitive to the life term, then biosignature research becomes important. If you discover that the final result is most sensitive to the length term, then understanding civilization risk becomes important. If you discover that the final result is most sensitive to the detectability assumptions, then broad technosignature work becomes important. This is how the equation can guide science even without being solved. Now we end with a simple, grounded summary of the story. Frank Drake did not write the equation to claim that the galaxy is full of neighbors. He wrote it to structure a conversation. He wrote it to turn a blurry question into a set of clear questions. Over the decades, some of those questions became measurable, especially the planet terms. Other questions remain open, especially the origin of life and the lifespan of civilizations. So the Drake equation remains a living framework. It is a bridge between the sky and biology. It is a bridge between wonder and method. And if one day we receive a signal, the equation will not be proven right or wrong. It will simply be updated. like a quiet notebook finally receiving new data. One last modern chapter belongs here, because it shows how the Drake equation can tighten over time. In the last few decades, exoplanet discovery turned the sky from a place of theory into a place of catalogues. We learned that many systems contain planets packed closer than Mercury, that super-Earths and mini-Neptunes are common, and that the solar system is only one arrangement among many. Then, atmosphere studies began. Scientists started measuring how starlight changes as it passes through a planet's air during a transit. They also began measuring the planet's thermal glow and reflected light in limited cases. This is still difficult work. The signals are tiny. Noise is strong. Interpretation is uncertain. But it is the direction of progress. Because the more atmospheres we measure, the more we will learn what kinds of worlds exist. If we ever find repeated signs of chemistry that is hard to explain without life, the life term changes from pure speculation to measurement. If we ever detect an artificial narrowband signal, the technology term changes from hope to fact. And if we never find either, after searching a large enough space with sensitive enough instruments, the equation will still do its job. It will tell us which assumptions must be wrong. That is the quiet power of a framework. And as a final gentle note, remember what the Drake equation does to the mind. It takes a huge question and makes it feel calm. It replaces shouting with terms. It replaces certainty with honest ranges. It gives us permission to be curious without pretending we already know. In that way, the equation is not only a tool for finding others, it is a tool for understanding ourselves, our place in time, and the fragile span of years where a civilization can look up, build instruments, and listen. So we end with the question still open, but held in a steadier way. How many voices are out there? We do not know. But we know what questions shape the answer. We know which measurements matter. And we know that every new planet found, every atmosphere measured, and every year of listening adds a small page to the file, one quiet entry at a time, until the ledger changes and the night sky answers back in a clear, undeniable way, across distance, across time, across the quiet dark at last. This was a quiet archive story, where the story ends, sleep begins,